In this section, what we're going to talk about here is solving inequalities, particularly polynomial inequalities. This is a really, really useful tool for those of you who will be taking Calc 1 at some point. A really necessary action that you have to do for that is to figure out where things are positive or negative, because they tell you a lot about behaviors of curves and models. So it is super useful for that class. For us, it's just going to be an algebraic thing we can do. So we're going to start with a quadratic inequality here, x squared minus 2x minus 15. What you'll see is that we can't really just solve for x here because of that square, because it is a quadratic. So it's not going to be like a linear inequality, really. We're going to have to use slightly different techniques. But what we can do is use some of the information that we know about this. We know what the graph looks like. It's a quadratic, so it's a parabola. And the lead coefficient is +1, so it'll be an upwards parabola. And we can do a really quick rough graph of this that's good enough for us by finding the x-intercepts. And the x-intercepts are just zeros. So we don't really have to use all the techniques from the previous section. We can just find the zeros by factoring. Yeah, so that's what I'm going to do here. Two numbers that multiply to -15 and add to -2 should be -5 and +3. So that's what we're going to look at here. Maybe I will rewrite the original function first. Yeah, so if we look at the graph of this, I'm not going to draw a great graph here, but what I know is that I've got my x-intercepts at -3 and +5. So let's just draw those. My -3 and my +5, and it's an upwards parabola, so the vertex should be somewhere in the middle. I'm not drawing any real scale here because I don't care to make it perfect. It's just enough to kind of see some behaviors here. And so if I'm looking for where this thing is greater than or equal to 0, what this means as far as my graph is on or above the x-axis. So that is going to be the points and then everything above it. That's what it means for the y values, or for the function to be greater than or equal to 0. And so what I've got to do to get my answer is to describe the regions that I see in that picture. And so if I'm looking at this, what I've got here is this section onwards. That's my 5 to infinity. And then over here, I've got that point inclusive, but everything to the left. So that'll be -infinity to 3. And so that's actually my solution. So it will be -infinity to 3 combined with 5 to infinity. And so everywhere in those regions, I should get something that's greater than or equal to 0. You could try it. For example, 6 is in that region. If I plug 6 in, I will get 36 minus 12 is 24, minus 15 is 9. It's bigger than or equal to 0. So that is one technique that we can use, but it's going to kind of lead us into a technique that's going to be a little bit more practical for functions that we don't really know what the graph looks like. So we'll do a second technique. It's just going to involve the factors with no sketch. So what I like to do for this technique is to construct a table . And in this table, what I'm gonna have here is my zeros are going to be very specifically, so they're not going to be headings in the table. What I'm going to do is write the zeros above the lines that separate the columns. So they're going to separate my columns. And what I'm also going to do is write them in increasing order. So they have to go left to right, basically. And then what I'm also going to do is list the factors along the side here. So x minus 5 and x plus 3. And then what I can do is basically just see what the behavior of these factors are, just with regards to whether they're positive or whether they're negative in these regions. So the regions that would be broken up here if I were to use these number lines, this section here is going to represent everything less than -3. So basically those numbers are just sort of splitting up our real number line. You can even label that as, if you like, as the real number line between -3 and 5. So that's going to be x's between -3 and 5. And then the rightmost section is going to be everything strictly bigger than 5. So we're going to exclude the -3 and the 5 from those regions because we actually know exactly how this function behaves there. It's 0 there, and that's why we chose those numbers. And so what we're able to do now is actually just kind of look at the behavior of x minus 5. So x minus 5, if I plug in a number that is less than -3, so I'm going to write in my ugly, hard to see yellow because I want it to look really rough. Just come up with an example number. I don't know, -5. That is a number that is less than -3. So if I were to plug in -5 in here, I would have -5 minus 5, and that is definitely negative. So that's going to be negative. In fact, every number that I plug in from that interval of x being less than 3 is going to be negative. If I plug in a number between -3 and 5, so say 0, then look what I get. I get 0 minus 5, and that's a negative. So that region there is also going to be negative, the whole region. And in fact, what you'll see is that the behavior doesn't change until 5. Now, this doesn't start becoming positive until we plug in numbers that are bigger than 5, like say 6. If I plug in 6, I get 6 minus 5. Well, that's positive. And so what I'm going to get is positive for this region. Now, I'll do the same thing for the x minus 3. I could try plugging in these numbers. -5 plus 3 is negative. 0 plus 3 is actually positive. And 6 plus 3 is also positive. And so, yeah, what we'll see is that x plus 3, when you plug in a large negative, it's negative. But at -3, that point where I've separated this number line, that's where this particular factor hops into the positives, and we're seeing that in the second region. And then when I start plugging in bigger positives, it's still positive. And so now what I'm able to do really quickly from this is use the fact that my polynomial is the product of these two things, this x minus 5 and x plus 3. So what I'm going to get here then is that for my final results, so I know you might be thinking this is taking a lot longer than what I did on the left, but the thing is I can use this in lots of other examples. So it has its benefit. So what I have here, this is the product of something that's entirely negative in this region and something else that's entirely negative in this region. Well, two negatives, despite what our parents say, make a positive. So we get a positive there. For the next one, we've got a negative times a positive. So we're going to get a negative, and a positive times a positive, and that's going to give us a positive. And so this is a relatively, once you get used to it, a relatively quick way to actually fill in this table and get all of our signs. And then that's going to answer this question for us. So the greater than or equal to 0, that means positive or 0. So positive means it's greater than 0. We should be able to just put our answers together here. Greater than 0 will be negative infinity to negative 3, along with 5 to infinity. The equal 0 occurs at those endpoints, the negative 3 and the 5. And so what we would do is just use that negative 3 and 5 to sort of close up those two interval ends. So negative, greater than or equal to 0, our whole solution set here will be negative infinity to negative 3 combined with 5 to infinity. And yeah, you'll see that we get, oh, sorry, those were, oh, I actually made a mistake in my previous answer, which I'm now just catching. I should fix that now. I just realized that my solution here, all the way down to that graph on the left and over here, hopefully you noticed that those should have been negatives, but a good thing I did it twice because I was able to catch that mistake. So yeah, so what I'm going to do now is give an example with a much bigger, messier polynomial, and we're going to see that this table technique is actually going to do wonders for us. All right, so what we've got here is a much more complex polynomial inequality. We've got x times x plus 4 squared times x plus 1 times 2x minus 7 is less than 0. So I have no idea what the graph of this thing looks like. And in fact, I can actually use this inequality that I'm going to get here to help me figure out what the graph looks like. So yeah, what I'm going to do instead of graphing, because I don't know what that looks like, is set up tables to try to figure out what the regions are going to look like, probably some intervals where we actually end up with something that's less than 0. All right, to get this one started, what we will do is, first of all, find the zeros. And yes, we just take that from all the factors. Don't forget the x there. I know a lot of people will just kind of overlook it because there's no brackets on it, but it is in fact going to contribute a 0 of 0. So we're going to get a negative 4, a negative 1, and 7 over 2. And so step 2, we're going to set up our table. And so that is going to require us to write those numbers in increasing order. So negative 4 is the least. Then I'll have negative 1, 0, and 7 over 2. And I'm going to set up my lines. Now remember that those numbers are going to go atop of these lines. They're not the column separators. They're just going to go above these lines. And the next thing I'm going to do is list all of my factors. I was very nice in this one, well, I guess mostly to myself, and then I wrote the whole thing factored out. I could very well have given this thing simplified, and then you'd have to do all the factoring. Then we're going to list the factors along the left. Make sure you give space for the x less than negative 4 section here. You don't need to label this, but it doesn't hurt to do so. -4 less than x less than -1. Yeah, so just make sure you leave yourself a little bit of space there so that we can write out those factors. That's kind of the biggest reason why I'm writing these column headings, is just so that I remember to make that space. And so my factors, I need everything. So x plus 4. I'm going to intentionally make a little mistake here. So the way that I've written it right here is actually not going to do me much good, because if I multiply these 4 things on the left, I don't get the function on the left-hand side of my example. I need the factors to match, and I need to include any multiplicities here. So if there's powers, I need to include them. We call that multiplicity. Yeah, so I should be able to do this without necessarily plugging in test numbers. I can kind of just do this in my head. I know that x is negative until I get to 0, and then it's positive. So, right, that should kind of make sense. This next one, because of that square there, actually everything is positive. The only place where that's not positive is at where it's 0, but that's already, we're not interested in that value here. So for x plus 1, that's going to be negative until we get to -1, and then it's going to switch over and be positive. And 2x minus 7, the 0 for that one is 7/2. So it's going to be negative until we get to 7/2. Now you could test some numbers in those regions to check, but this should work out. And then if I plug in a number bigger than 7/2, say 4, you can see that we should get a positive. And then to work this out, it should be relatively quick. It's just kind of counting negatives. 3 negatives leaves a negative. 3 negatives leaves a negative. 2 negatives are going to cancel and give us a positive. And that's the reason why 3 will give us a negative, because 2 of them will cancel. 1 negative leaves you with a negative, and all positives will leave us with a positive. And so finally, we can wrap this one up. To answer our question of less than 0, that means negative. So we're looking for just those negative regions. And yeah, we basically just need to describe them. Notice this one is strictly less than 0, so I don't want to actually include any of those endpoints. So what I'm going to get here is the first one, which is -infinity to -4 right here. And then the next one is going to be -4 to -1. And there's no overlap, though. Those two regions aren't connected because we actually have to skip that -4. And then finally, the last one will be 0 to 7/2. And that is our solution set. So that is a relatively quick way using these tables to basically get your answers. So that's all I'll do for the polynomial examples. In the next video lesson, I'll do some rational ones as well.